Hey everyone, this is Dr. Walker. This is video 232. It's called ohmic and non-ohmic devices. First thing we want to do is look at what is the difference between these two types of devices. An ohmic device is one in which the relationship between current and voltage is linear. As you can see in this graph, as the voltage is increasing, the current is increasing. And this comes from Ohm's law. I equals delta V over R. As the voltage increases, the current increases. So ohmic devices follow Ohm's law. And a really good example of an ohmic device is a resistor. What about non-ohmic devices? So non-ohmic means that the relationship is nonlinear. You can see here, as the voltage increases, the current increases, but there's not a linear relationship. It starts to increase, the current starts to increase more and more as the voltage increases. A good example of that is a diode or a light bulb. Sometimes there are some labs associated with this where you can see that when you plot the current and voltage across a light bulb, that you don't get a linear relationship, so a non-ohmic device. So the only other thing in this section is interpreting this graph. We have the current through a wire is measured as the potential difference is varied. What is the wire's resistance? So this is something that is done in some college physics labs where you have a wire or a resistor and you keep increasing the voltage, and each time you measure the current through the circuit and then you plot the points and it's going to form a line. And what you do is you put a line of best fit through those points. And then you can interpret this data and get the resistance of your resistor. So how do we do that? Well, we use the fact that we do have a linear relationship between the current and the voltage. Y equals mx plus b is the equation for a straight line. And then Ohm's law is I equals delta V over R. So what we can do is we can rewrite Ohm's law so that we have 1 over R times delta V. And the reason that I rewrote it like this is because then we can compare it to this equation for a straight line. The y-intercept is 0. So we can cross out the y-intercept. So we have y equals mx, and we have I equals 1 over R times delta V. So we know that the y-axis is the current, and the x-axis is the potential difference. So that means that the slope of the line, the m, is equal to 1 over r. That is what our analysis tells us. The slope of the line is 1 over r. So if you solve for r, it's equal to 1 over the slope. And that's what it says on this graph here. If you have a graph of I versus delta v, then the inverse of the slope will give you the resistance. So let's go ahead and calculate that here. Let's pick 2 points on this line so that we can get the slope. So 0, 0, and then 50 for the y and 1 for the x. So the slope is change in y, right? Rise over run, change in y over change in x. So the rise is 50, and then the x is 1. So the slope is 50. So 1 over the slope, 1 over 50, is going to equal to 0.02 ohms. That will be the resistance for this data, for this graph. So I just want to show that it's something a little bit different from what we've done, but you may see it in a lab class someday, so it can be useful.